Good morning, ladies and gentlemen at the ADC. My name is Hao Hao, and thank you for joining me for my talk today, which is titled Parameter Inference of Music Synthesizers Using Deep Learning. First of all, a little bit about myself. I'm a music tech enthusiast currently based in Singapore. So unfortunately, I can't be in London today with you guys, which is quite a sad case, but hopefully I can see you guys sometime in future in person. For me, I'm particularly interested in the intersection of AI, ML, and music. So previously, I worked on topics such as music generation, cover sound detection, music fingerprinting, and audio synthesis. Today, I will do something a little bit different. I'll talk about synthesizers and parameters. Yep. So as we all know, music synthesizers are everywhere in today's music production pipeline. And finding the correct parameters in order to shape the desired sound become a very important process for many producers. So today I would like to share a bit about how we can use deep learning to facilitate the sound design process. Yep. So moving on to my next slide. Before I dive into the details, I want to share a bit about why I'm interested in this topic. So I learned sound design like a few years ago, and when I first learned about it, and this is the user interface I first encountered in the course. This is my first synth. And the first thing that came to my mind is, holy crap, there are so many knobs on this thing, right? So I'm a novice, I don't know what to do with it. There are too many knobs that I can control. But of course, looking back, since like silent don't really have the most number of knobs for you to tune, this is like a pretty standard thing. But no matter for novice or for professionals, I think there's still a certain amount of parameters that you need to take care of when you're doing sound design or you're using synthesizers. And later I learned something called the presets, right? I believe quite a lot of people love presets. Presets are basically some set of parameters that professional sound designers come up with. So what you can do, you can just download it, lazily load them into your synthesizer, and you just have your sound that you desire. You don't need to tweak it. You don't need to go through any hassle of designing. Just use it as it is. So I fall in love with presets, and I have a lot of presets. Then an idea came to me is, why not we train some kind of model that given any sound that you have, it can just output the synthesizer preset for you, right? And you can just load it into your synthesizer without tuning, without searching for presets online, and it will be very good. It will be easy to use. So that is basically the motivation behind this topic. It's called Parameter Inference of Music Synthesizers. So I'll probably give a quick demo of what it actually means. So let me just share my notebook. If you guys can see my notebook here. So basically, I have some code running around. Basically, it's a library that I've written called Syntheon. If you click on it, of course, this notebook will be shared with you guys. So yeah, it's basically some GitHub page, yeah, blah. It's basically a library. And the synthesizer I'm using here is Vital, which is the Wavetable synthesizer. Last year, there's a talk by the author. It's himself, that title. Great talk, shout out to him. Yeah, and basically, we have a use case like this. So let's say today you listen to some plug sound or some lead sound that you like. So let's try this one. So yeah, so what you do is you have this library, and basically you will do infer parameters. You basically just put in your audio file, your synthesizer name, and things like that. So let's just run it a bit. Okay. It probably will be slow right now because I have Zoom and all those things running and in the background. Yeah, so just give it a little bit of time, if you guys may. So what it does is actually, first of all, it will infer your fundamental frequency from your audio, and you will do some feature extraction, things like that, and you'll load it into a deep learning model, and it will just give you the parameters. Yep. So I have basically my preset here. So right now I'm going to GarageBand and pull out my Vital. Just give you a little bit of time. Yep. So if I open the preset, yeah, it's basically this preset because just now I was testing it. So basically, it kind of infer that you have a very plucky ADSR, and then you have some kind of a triangular wave. So let's try and see how close it is. Oops, I hope it's hearable in this in the hall. Yep. So if you compare it back to what you have here, yeah, it's pretty close. And basically, this library can tell you a measurement of the spectral loss. Basically, it's how close your parameters can recreate the sound. So maybe let's try another example, which is on a sustained sound, which is like a lead. Okay, and then let's run it through again. It's getting slower and slower. Yeah, later we will talk about like how we can actually train the model or use different kinds of features or different kinds of parameters and how we can model them using deep learning, right? So yeah, now we have it. And then if you go to GarageBand again, yeah, it should change. Yeah, so now you can see the ADSR changes because it's a sustained sound. You have a longer, I think it's just you have longer decay, higher sustain as well. And then you have your waveform here. So let's try and see how close it is. The notes should be. Yep. If you listen to the original one, yeah, it's quite close, but of course you can still tweak a bit, and it's also seen in your spectral loss. It is slightly higher than the plug sound that we have just now. So basically an idea for you guys about what parameter inference is and how you can use it basically. So right now, let's dive it back into our slides. Yep, it's here. So yeah, I have a project link here. Basically, if you guys are interested, hit me up or have a look. Yeah, let's talk about synthesis methods right now. So before we talk about the methods and things like that, we need to understand some major synthesis methods. And basically, different synthesis methods cares about different parameters. The first one, I'm going to talk about additive synthesis, which is quite a popular one. Additive synthesis basically assumes that all sounds are some kind of weighted sums of signals. So if you just take sinusoids as a very simple case, basically you can think of one sound being a sum of sinusoids of different frequency partials, and then you have some weighted average of them. So you can basically express it using this formula where you have your sinusoid, you have your frequency partial, you have a phase offset, and then you have your amplitude envelope over time. Additive synthesis is one of the widely used methods, and particularly additive plus noise is pretty much a robust model because you can model the harmonic parts in your sinusoids, and you can model the inharmonic parts using a noise. The other one is a subtractive synthesis. So basically, it's the opposite of additive synthesis, where you start with a waveform with very rich frequency partials, like you have your sawtooth, your square, or your noise, and then you just apply a series of filters to remove the unwanted frequencies that you don't want. So you can apply a bunch of low pass, high pass, or band pass, or different kinds of filters. And then in the end, you have the final output of your sound. So here, the parameters that we care about are mostly the parameters of the filters. So pretty much your frequency cutoff, your resonance, and things like that. There's also wavetable synthesis, which is what Vital we have just now. So for wavetable synthesis, basically you have a fixed size, fixed length wavetable. The wavetable itself is a parameter. So you can actually learn that, you can actually tune that. And then what you have in wavetable synthesis is basically your phase accumulator. So you can just think of it in simple terms, you're looping across this wavetable, and then it's a modulus function. So once you hit the end, you just come back to the start. And then basically, if you have a higher frequency, you basically loop across this wavetable faster. By looping faster basically means that within one time step, your sample increment is going to be larger if you have a higher frequency. So which you kind of jump more to the next index within your wavetable, right? One thing to note that is because when you jump always, when you're finding the index of your next sample within your wavetable, the index is not always going to be integer. So sometimes you can come up with indexes something like 2.3 or 3.6. So it's a fraction. So once you hit a fraction where you know that we can't have fractional index in digital waveforms, so what you do is you need some kind of interpolation. So probably the simplest one would be a linear interpolation. So you can just get the sample from front and the end, and you just kind of guess what is the amplitude of the sample in the middle. So there are also other interpolation kernels like cubic. Of course, we can explore that. The next one, which is one of the popular one, is also FM synthesis. So for FM, basically within an oscillator, you have two frequencies. One is called a modulator, one is called the carrier. So basically the modulator will output a frequency that will change or modulate the carrier. And the output of the carrier is basically a final output of your sound. So basically here, one of the important parameters is actually a modulating index. So it basically defines how much the modulator is going to modulate the final signal. So if you look at here, if this modulating index equals to 0, then basically here you can see you don't have any modulation. So you only have the only frequency partial is your carrier frequency. But if you start to crank up your modulating index, then basically you start to have different frequency partials coming in the intervals of your modulator frequency. And basically the nerdy term for the amplitude here is basically called the Basel's function of the first kind, which we are not going to delve deep in this talk today, but feel free to look at it if you're interested. Another thing which is important is also the FM configuration, which is how you connect different oscillators together, because we know that one's carrier can be also the other's modulator. So you can kind of think of different configurations of how you want to connect or route your different oscillators. So, and different types of routing or different configurations together with different modulating index will give you a very different sound texture, which is kind of similar to some of the instruments that we have. Yep. So basically, I want to highlight these 4 methods. There are, of course, many other synthesis methods like granular, wave shaping, physical modeling, things like that. I will not talk about them today due to time constraint, and also not a lot of work has been done on these parts. So we'll focus on these 4 in today's talk. Yep. So let's talk about parameter inference. So why do we need parameter inference? As we've seen it from the demo just now, probably it has some value add actually for both amateurs and professionals. For amateurs like me, I would think it makes my life much easier, right? Because you can just crank it in, load a preset, and you can just do whatever you like. So sound design will be made much easier with an inferred preset to start with. And also it has a potential of being an educational tool to learn sound design. For professionals, sometimes I talk with some music producers, they say they don't like doing sound design because it's too tiresome. Yeah, and too boring for them. Yeah, so probably in this case, it will save you some time. And of course, if your model can learn something like a latent structure or latent representation, which tells you the mapping of your audio and parameter, actually you can traverse this latent space where you can discover different audios with very different parameters and very exciting sounds. And that can also be a very exploratory and interesting experience for professionals. Yeah. I have run through what are the parameters, but let's just revise it a bit. Normally, if you're talking about software VSTs, oftentimes you have kind of like 2 pages. One is basically your oscillator part, and the other part is your effects part. So for oscillator part, the common parameters we have are your ADSR, your oscillator level, your wave type. For FM, you will have your modulation index, your FM configuration. Yeah, for wavetable, don't forget your wavetable itself is a parameter, and then you have a phase offset. And then for filters, you have your cutoff frequency, your resonance, things like that. And for effects, actually, it's a wild west because we can have all kinds of parameters in our effect. Yeah, but the most important one would definitely be your mix level, basically your dry web knob for your effects. And then just for some example, for compressor, you have a compression ratio, threshold, attack release. For reverb, you have your reverb size. For EQ, you have your bandwidth, your gain level, your cutoff. Basically, you have lots and lots of parameters that you can actually model on. Yep. Before I dive into the deep learning part, I want to just give a shout out and some reference to some parts work on parameter inference, but you're not using deep learning methods. A very big part of them has actually used genetic algorithms because it's quite popular in like 2000 and 2010s. Basically, you just do some evolutionary algorithm to just shorten or shrink your candidates such that finally you get some presets that you can use. So that's the idea behind using genetic algorithms. There are also some other methods like Gaussian process, particle optimization. So if you're interested in them, do have a look in these papers. Yep, so let's talk about deep learning in this case. I'm sure quite a lot of talks I've seen in ADC has covered deep learning, but I'll just cover some basic concepts so we are all on the same page. Yep, so basically deep learning is a branch of machine learning. Machine learning basically means that given the input data and some output that you want, you try to learn based on data-driven methods on the underlying structure or underlying mapping between them. And basically deep learning is just machine learning with many, many layers of neural networks. And what are neural networks? Neural networks are basically just function approximators. They are very, very good function approximators. They have a large number of learnable parameters. So given the optimization process, it can learn very complex function mappings. And in deep learning and machine learning, basically you have different types of learning modes. So basically we call them supervised, unsupervised, or semi-supervised, right? So for supervised, basically you have your input data and a label. So basically you feed your input data into your network and then you will output something called your fx. And then you want to calculate your loss function, which is basically a distance metric between your fx and your actual label y. And you optimize according to this loss function. For unsupervised case, you don't have any labels. So what normally we do, our objective function will somehow include your input x. So one very popular formulation is actually to reconstruct x. So you want the neural network to be able to reconstruct itself. So this is one way that we don't need labels where you can learn something meaningful. There's also semi-supervised. So if you can do both, why not, right? So it's a combination of the best of both, and commonly the objective function is a weighted sum of both modes. Why we need semi-supervised is because label data is very hard to get, especially in music case. I'm sure if some of you guys have done some work on this, it's super hard to get quality labeled data for music cases. So somehow you can get some of them, but then you try to use some unlabeled data to kind of improve your model performance. There are two keywords in deep learning, which is gradient descent and backpropagation. It's worth a chapter to talk about for this one, but just to give a very high level view. So normally you have 4 steps to train your neural network model. So first of all, you need to do a forward pass. What we mean a forward pass is you just put your input into your entire neural network, which is basically a bunch of functions, and then you basically have an estimated output. This is your first step, which is your forward pass. The second step is to calculate your loss. So basically you have estimated output. So crank it in with your actual output and then just put it into your loss function and calculate how bad or how good you're doing. The third step is called a backward pass, or normally we call it a backpropagation. So basically what you need to do is you need to calculate all the intermediate derivatives of each of your states, and then you need to backpropagate these derivatives, or we call the gradients, back to your learnable parameter. So as we all know from chain rules, so all the derivatives of the intermediate states are all just a product of the states from the right side. So we can just do a chain rule, which is calculating products of all of these derivatives up to your learnable parameter. So basically here. So the final step will be your update rule. So basically it's like this in these 2 boxes. So you want to update your current value of your parameter with a fraction of the derivative or the gradient that you have just calculated. And the fraction here, the alpha, is normally what we call the learning rate. It defines how fast or how slow you want to update your neural network. Yeah. So one key concept here is differentiability. So if all the gradients can be calculated and if they can be backpropagated to the learnable parameters, then we say that this component is entirely differentiable. So basically you can calculate and you can train this module. And we will revisit this idea when we talk about differentiable DSP in a future slide. Yep. And of course, we know that we have very different neural network blocks, from the simplest one, the MLPs, which is basically just stack layers of neurons. And then you have the famous convolutional neural network, which basically just run convolution operations across 1-dimensional or 2-dimensional data like image or audio. Then you have recurrent neural networks, basically is very good for sequence data because you are passing through hidden states across each time step of your sequence. And lastly, we also have something called the temporal convolutional network, where they use something called a dilated convolution. So dilated basically means that your kernel or your filter basically is spread out. So you can see this green layer or this red layer. So they are all Windows filters with Windows size 3, but it's like spread out. So once you have this spread out kind of structure, you can actually incorporate longer sequence or longer structure information within your learning. So it is also good for using it for like sequence data. And actually it's quite popular for some audio related tasks, and all of them kind of use TCNs and they perform quite well. Yeah. The important question is actually why use deep learning for parameter inference? Why? So we have so many methods. Why deep learning? One reason is because neural networks are very good at learning highly complex nonlinear mapping functions. And we know the mapping from your audio space to a parameter space can be highly complex. And we don't really know what is the underlying distribution. And neural networks are very good at learning this kind of stuff. And following a study done by Matthew Yi King in 2016, he basically draws two conclusions, and he benchmarked different methods on the task of parameter inference. So basically, he finds that in terms of performance, deep learning methods can outperform other methods. So it's seen in these tables here, basically. And one important thing is inference speed. So let's say if we are using like a search-based method, like let's say genetic algorithm, you need to search such that in the end, you can converge until you find the best candidate. And that takes around 40 milliseconds in terms of latency. But then for deep learning, it's basically an artifact. You already have a compound model in the end. So once you want to do an inference, you just need to do a forward pass, and the latency is going to be close to real time. So that is kind of one of the cutting edge advantage of why we want to use deep learning for parameter inference as well. Yep. Let's talk about some of the formulations on how we can formulate the problem of parameter inference as a machine learning problem. And one obvious one I would say will be to formulate it in terms of supervised learning. It's pretty simple. So basically, first of all, you need a data set, which on one side you have your audio samples, and on the other side you have the parameter values that can give you or synthesize this audio. So be it your wavetable, your oscillator levels, your envelopes, and things like that. And basically, once you have these pairings, you basically have a data set and you're ready to train on it. And the training will be pretty straightforward as well. So what you can do is first you can choose a model that you like. Normally, a lot of work actually choose CNNs or RNNs or TCNs, basically audio related networks, due to the reason because CNNs and TCNs are very good at doing convolution and aggregating long-term info, and RNN as well because audio is basically sequence data, right? So how you can do it is basically you can either choose to pre-extract some features from your audio, so basically like spectral features, or you can also just feed in your raw waveform into your model and just let it learn some intermediate representations. And then depending on your parameter, if it is a continuous parameter, then you can pass it through some sigmoid layer. So you map your output or final values between a range of 0 and 1. So if it's a discrete or categorical parameter, you finally just put it into a softmax activation and you just tell it the probability of different states. And once you have the estimated parameters, pass it into a loss, and calculate your loss function, and then you just backpropagate. So pretty simple and pretty straightforward formulation for supervised learning. One thing to note is how can you build your data set? Actually, quite a lot of work just try to build by their own. So they try to find a way to automate the process of synthesizing audio using synthesizers. One way is, of course, you can write your own synthesizer, which is pretty painful. But a lot of work actually does that. I personally do that for Syntheon. And the other one is actually there are some synthesizers, some automation tool, and I list down here. One is RenderMan and one is DawDreamer. And what they allow you to do is you can just load VSTs into Python runtime, and you can do all kinds of manipulations on this VST just using Python code, and then you finally can synthesize that audio. So this really allows you to synthesize audio based on some synthesizer, commercial synthesizer that you want to model the parameters on. Yeah, and of course, one way is of course to get it online to see if someone make a preset bank or just purchase it on Splice. That will be one way to build a data set as well. So for Syntheon, basically the parameters I infer are the wavetable and your ADSR values. For the wavetable part, actually, I tried to directly infer from the audio itself, because as we know, like for quasi-periodic signals, basically you can just find a period within your signal, and then that period actually can be a good approximation for your wavetable. But of course, we can still tune it using some other ways, but it will be a start or a good approximation for your wavetable. And then for the ADSR, basically, I just generated 100K audio based on some fixed set of wavetables and with random values of ADSR. And then what I use for features is I use the loudness as a feature, and then I just pass in through a GRU, which is basically a variant of a recurrent neural network. And then I can predict the actual ADSR seconds, where I can translate it back into a vital preset format. There are other works that's been done. One is called Inversint, and this work particularly writes its own synthesizer in Java, if I'm not wrong. It's called Json. And then this synthesizer is basically an FM-based synthesizer, where you have 4 different waveforms with your carrier and your modulator and your amplitudes for each. And then you have your ADSR, and then a low pass filter and a noise gate. So if you count here, there is around, I think, 23 parameters that you can model upon, where you can use the supervised method just now to predict it. So if you look at it, normally for the parameter inference part, the authors actually propose using CNNs. But the interesting part is they choose either to extract the spectrogram, pre-compute the spectrogram, or they can just pass in the raw waveform into a few layers of 1D CNNs, and then you can use the final learned representation as your feature maps. And if I'm not wrong, the authors actually find the second method to perform better. So it's always the case in deep learning where you can just try to do some kind of end-to-end learning without using some features. Yeah. I want to give a shout out to Serums RNN. So this is a work done by Christopher Mitchell-Tree. He gave a talk yesterday on Newton. So shout out to Chris. This is one of the few works that actually focus on effects and not just the oscillator parameters. And not just effect parameters values, but also the effect chain itself. So the idea here is, of course, in Serum RNN, you have the parameter model, which basically, like the models before, you predict the actual values of the parameters. But also, this RNN can give you the effect chain on how you can get to your final audio output. So to give an example, in this case, basically for his data set, he add up to 5 effects. So you will start from time step equals to 0, where you don't have any effects being applied. So you just extract your features, your Bell spectrograms or your MFCCs, and then you just pass it in into your LSTM. The LSTM is going to tell you what is the first effect that you can apply. So what you need to do is you pass through your model, you know what effects you apply, and you apply it on your audio. Let's say it's a reverb. And then for the next time step, you extract the audio features of the reverb audio. And now you have the MEL spectrograms and MFCCs or your reverb audio, put it into your LSTM again. It's going to tell you what's the next effect that you should apply to get to your final output. So maybe it's a phaser. Then you go on and you go so on and so forth. You iterate this process, and finally you will see you can get an effect chain. And I think this is really interesting because it can be used in many use cases, not just in synthesizers, your plugin chains, your vocal chains. You probably will land into the very similar idea of using the idea of serial RNN to learn this kind of effect chains. Yeah. There are other works as well, which are cool work, I would say, but due to time constraint, I will not run through each of them. Some of them use some probabilistic learning, and some really learns a deep latent space for you to traverse so that you can explore the audio in between. So do check out some of them. Yeah. The next chapter, I want to talk about semi or self-supervised learning. So one might wonder, if I want to learn parameter values, how can I do unsupervised learning just on the audio itself, which is pretty interesting. So let's look at the formulation. So right now, think of this case that you don't have any presets, you just have a bunch of audio and you don't know what to do. So what you can do is you can extract, first of all, the fundamental frequency of your audio. And as usual, like the supervised chapter, you can extract the features, put in your model, get the estimated parameter values. But right now, you don't have any presets. You don't have labels to train on. So what you can do is you can just feed these parameter values as a preset to your synthesizer, right? And then you have your fundamental frequency, so you know how you can play your synthesizer. So you can feed that into your synthesizer as well, and use these to synthesize a final audio. And what actually you want is your final synthesized audio to be as close as your target audio itself. So it's like a surrogate here. So you still can train. So the training objective function will be your audio spectral loss. So you want your synthesized audio to be to mimic your target audio. So the idea here is the better your synthesized audio gets, it also means that your parameter values are more accurate. And this is how we can train to get an accurate parameter value set as well. So in this case, you can see, hey, we don't need any presets as well, right? So it's pretty cool, and all kinds of audios can be used for your training. Yeah, but there's a problem, there's a catch. We talk about differentiability just now, so you need to backpropagate the gradients. But all your VSTs, like your synthesizers, all of them are not differentiable. They can't backpropagate gradients. So how do you solve this problem, right? So this comes to something, a concept that's very popular recently. It's called Differentiable DSP. It basically means that for all your DSP components, for all your operators you use in DSP, try to implement it or write it using some automatic differentiable or the differentiation library like TensorFlow or PyTorch, where your add function, your convolution function, all of them actually can do a backpropagation. And by that, you basically can implement some differentiable synthesizer or differentiable audio effects like differentiable reverb. Everything is differentiable. And once this part is basically differentiable, then we basically solve the problem of backpropagating our gradients. And this also allows us to do end-to-end learning. But there's downside, of course, because now you have to write your own synthesizer, which I can guarantee you is pretty painful. So you have to rewrite every component you need, such as it's differentiable. But basically, this is kind of the trend of the current work that's being done. There are some ideas on how you can do something like a gradient approximation, where you can just treat this as a black box, and then you can just try to calculate some gradient, you approximate some gradients here and backpropagate from here. I'm not too aware of that, but I know that there are some works that have been done. So, but we are not going to talk about that in this work. So we'll talk about DDSP in this case. So just to give an example, for example, this is an implementation of a wavetable oscillator in PyTorch. So you can see that basically for all the operators here, they are all differentiable. So which means, let's say you want to train a learnable wavetable, which is you want to learn the wavetable from an audio segment. So you can just calculate the loss function from your output. And basically because it's, okay, so basically because this is differentiable, you can backpropagate the loss here until your wavetable, and you can learn basically your desired wavetable of your audio itself. So there are some work that has been done. One is called DDX7. It's done on DEX, but actually it's not directly on DEX. Actually, the author wrote his very own differentiable FM synthesis as well. Basically, what he wants to model is actually not the configuration. Basically, in this case, the authors fix the modulating index and also the configurations for each of the different instruments. But what he wants to model is actually the output level of the 6 oscillators. So basically the amplitude of each of this, and it can still shape the final sound. And the data set it trains on is now, you don't need any parameters as well. So you can just train on something called the URMP data set. It basically consists of recordings of violin, flute, and trumpet. And how you train is basically what I mentioned just now. You extract the pitch, which you can control your FM synth, and then you use some features such as, in this case, loudness, pass it through your neural network. In this case, they choose TCN, and then you have your oscillator envelopes, and you can load it into your FM as a preset. And in the end, you basically just do a multi-scale spectral loss between your synthesized audio and your target audio. Yeah. And there's also one work which uses semi-supervised learning. If you remember what I said about semi-supervised learning previously, is if you can do best of the worlds, why not both? Yeah. So this is the idea of this work. So what they did is, firstly, they do a pre-trained manner. So basically what we discussed about everything in the supervised chapter. So train a model using parameter loss, things like that. But then what they discovered is that you can use unlabeled data. In this case, they use NSYNC. NSYNC is basically a data set with just one single note recordings of different instruments. And basically they find that using an unlabeled data and you train it using the differentiable spectral loss reconstruction manner, it can actually improve the quality of your synthesized sound. So this is something really interesting, because what they actually argue is that if you only train on in-domain data set, your synthesized sound will be very unnatural because you're only overfitting on some data set that you curated. But if you use real-world sounds, then your synthesized sound can actually serve more purpose other than the in-domain data set. So basically, this is the idea of using semi-supervised learning. Yeah. And basically some discussion on this task. So there are actually some gaps between using this in real world cases actually. So there are a lot of sounds. We know that there are so many kinds of sounds in the world. And there's particularly some sounds that actually involves modulation. So producers love to use like LFOs or macros to create some kind of like warping sounds. And right now, not a lot of work actually tackle the modulation part yet, because actually detecting modulation within a sound can be actually challenging as well. So there's something we can look into. There's also polyphonic cases. So right now, a lot of work like the demo I've shown to you just now is mostly monophonic and basically just on single notes. The reason is because polyphonic is difficult. It basically needs music transcription and accurate transcription, and it's a very difficult problem in music information retrieval. But in polyphonic cases would be very useful, because let's say you're designing a sound for like soundscapes or ambient sounds or like chords, then actually having polyphonic detection will actually be very useful. There's also something that we discussed just now, which is implementing your own DSP modules are very troublesome. So we are in need of finding some alternatives on how we can train on parameter inference using some self-supervised methods. Yeah, I'm closing the end of my talk today. So just to give a very quick summary. So parameter inference of music synthesizers are useful for simplifying the parameter tuning process when we are crafting a desired sound profile. And in the deep learning context, we can formulate the problem in 3 different ways. The supervised way, which is the standard way, minimizing the parameter loss. The self-supervised way, where in this case, you need some differentiable synthesizer, and you can minimize the audio reconstruction loss. And finally, the semi-supervised way, you can combine both, where you can use some labeled data as guidance, but you can use a massive amount of unlabeled data to further improve your performance. Yeah. Finally, I want to just put some references here and some shout outs. There's one, if you're interested in learning more about deep learning in the audio world, 2 years ago, there's a great talk by Russell McClellan. And basically he delves in a lot deeper about how some details of deep learning and how its applications in the audio software. There are 2 titans, Matthew and Jordi, who actually have studied this problem previously during their masters and PhDs. If you're interested, do go through their thesis. And then Jordi actually have a project called SpiceLib, which is pretty much similar to Syntheon. And basically the models there are the models that are proposed by Matthew. Yeah, so if you guys are interested, do check it out. And of course, parameter inference is not just for synthesizers. You can do it for plugins, filters. There are endless possibilities, and recently it's a trend that's going on. So there are recent papers that are actually doing some parameter inference on filters as well, which is pretty interesting. Yeah. So I have reached my end of my slides. So thank you very much for your time. I would love to take on any questions in discussion regarding this topic. Once again, thank you for your time. Thank you very much.